Go ahead and start the recording, George. All right, everybody. Welcome to day 3 of the technical track. Today, we have an exciting keynote by Sean Lee. That's what's going to start off the day. After that, we'll have a short break. Followed by that, we'll have the award ceremony where we'll announce the best paper award, and a number of other awards are lined up, including the Test of Time and the Barbara Award. After that, we'll have the remaining parallel sessions, as you can see over here. And at the end of the day, we'll be closing out the technical track, but we still have the tutorials and workshop tomorrow. GatherTown is still available. It's in limited edition count. So when you have the opportunity, do hop on in and interact with your colleagues. As a quick reminder again, the keynote, when you're asking questions, feel free to type in questions in the Zoom question and answer box, not the chat box. Type your questions. If you'd rather ask the question live, say ask live, and we'll promote you to a panelist, and you can ask the question live. And as a quick reminder again to all of the paper sessions, the session chairs, use the Zoom Q&A or promote panelists. Questions. The sessions are 5-minute live presentations by the speaker and 10 minutes Q&A. Okay, with that, it is my great pleasure to introduce Sean Lee, who will be giving the talk today. Sean is a co-founder and chief hardware architect at Cerebras Systems, which builds high-performance machine learning accelerators. Prior to Cerebras, Sean was a fellow and chief data center architect at AMD, where he was responsible for the architecture of the C micro line of distributed servers. Sean's got a lot of interest in high-performance computing, architecture, hardware software co-design, and machine learning accelerators. And he will be sharing about the work that's going on at Cerebras today. So Sean, please take it away.
Thank you for that intro. Let me share my screen. Can you see the slides?
Yes.
Yes. Great. Thank you very much. So I'm Sean. I'm co-founder and chief hardware architect at Cerebras Systems. We started Cerebras with a vision to drastically change the landscape of compute for AI. And today I'm going to share with you some of the outside the box thinking I believe is necessary to meet the demands of ML in the future. For those of you who don't know us, Cerebras began in 2016, just at the beginning of the modern deep learning era. And our mission is to solve the problem of AI by building a full AI accelerator solution from chip to system to software. And now we have engineers and customers all around the world. And what an incredible journey the last few years have been, both for us as a company and, as I'm sure you can agree, for the entire ML community. But I'm here today because we believe we're just at the beginning of what neural networks can do. And we're already reaching a pace where traditional approaches can't keep up. In 2018, state-of-the-art neural networks had 100 million parameters, and that was a lot. But in 2019, models like GPT-2 and Megatron, they were 10 to 100 times larger. And last year, we got GPT-3 with 175 billion parameters. And in fact, just last week, Microsoft announced their Megatron Turing NLG model with 530 billion parameters. And there's no end in sight. Tomorrow, we will want to run models with trillions of parameters. That's 1,800 times more compute in just 2 years. Let me say that again. That's 1,800 times more compute in just 2 years. As a computer architect and for us as a community, I think this is both exciting and daunting at the same time. So let's take a look at how we've responded to this unprecedented demand from these new ML workloads. The exciting part is that we as an industry have been hard at work and we've seen some remarkable innovations. In fact, those models I just showed you, they wouldn't have been possible without some of these. And here are a few examples. In just the last few years, we've been continually improving on the process technology side from 16 nanometers to 12 nanometers, and now 7 nanometer chips are used every day. We've seen advanced packaging technologies to enable higher bandwidth memories and lower precision numeric formats such as FP16 and BFloat. And we have new data path designs such as systolic arrays and tensor cores that improve compute density and power efficiency dramatically. Let's take a deeper look at these improvements, starting with the process side. On the right, I've plotted the transistor density of GPUs over the past 10 years or so. And as you can see, the process industry continues to improve at an incredible pace. Moore's law is not dead. And we see this trend continuing for at least the next few years. Next, let's look at the other innovations. And broadly speaking, I'm going to group all of these into the category of architecture and microarchitecture. On the right, I've plotted the metric peak flops per transistor, again for GPUs also over the last 10 years or so. And here I'm using that metric flops per transistor as a rough measure of architecture performance. And what's impressive, as you can see, is that there's a very healthy increase and trend over time. In fact, it's keeping up or even slightly outpacing Moore's law by a little bit. For us as an architecture community, this is really refreshing to see because architecture matters. Now that's the exciting part. If we look at the last 2 years, we got about a 2 times improvement from process, from Moore's law, and we got about a 3 times improvement in architecture performance. But now comes the daunting part. In the last 2 years, from BERT to GPT-3, as we just saw, the ML demand increased 1,800 times. That's a 300 times gap. How do we meet that need? Well, it came from system scale out. And in fact, when OpenAI trained GPT-3, they used 1,000 GPUs. So when you step back, the performance gains over the last couple of years have been dominated by system scale out. So the answer is just scale out, right? The ML demand certainly doesn't appear to be slowing down. So you might think that we can just rinse and repeat the last 2 years and satisfy the demand from the next 2 years, right? Well, let's imagine what that might look like. Another 2 times improvement from Moore's law. We do have 5 nanometer and 3 nanometer in the pipeline. Another 3 times improvement from architecture, maybe higher density compute data paths, maybe different numerics. And then lastly, another 300 times from system scale out. Is that possible? That would mean clusters with the order of 100,000 chips. While that's not technically impossible, I think we can all agree that that's not practical. Just the sheer cost, power, and physical footprint would be prohibitive. And perhaps most importantly, it turns out that existing scale-out techniques are not easy to deploy and also not actually that scalable. And the reason is that fundamentally giant neural network models use massive memory, compute, and communication to tie it all together. And trying to provide all of this with thousands of small devices turns the scaling of all 3 of these into distributed problems that are interdependent. It becomes an explosion of distribution complexity to get them all to work together to solve a single problem. And this complexity grows dramatically with cluster size and becomes quite overwhelming at large models. So instead, for all of these reasons, with the existing scale-out techniques, I think there may be another 10 times improvement, but not much more practically. So that would give us cluster sizes on the order of 10,000 chips, maybe. And in fact, we're seeing some evidence of that already. Last year, GPT-3 was trained on 1,000 GPUs by OpenAI. And Microsoft's announcement last week is that they trained MTNLG on 4,000 GPUs. But I believe this scale-out trend will not continue much further with existing techniques. So where does that leave us? With the existing approaches, the industry possibly has a path to another 60 times improvement in the last 2 years. Sorry, in the next 2 years. But as I said, we need order 1,800 times. And that is the grand ML demand challenge in front of all of us. We must find ways to substantially improve across the board, to improve process technology beyond Moore's law, to improve architecture by orders of magnitude, and to improve and simplify scale out substantially. All of this is required for us to have any hope of keeping up with this ML demand. So imagine a world where scaling is more balanced, where we can get another 10 to 50 times improvement on process and on architecture and truly scalable clustering. Is that even possible? We believe it is, but only if you think about the problem differently. By thinking outside the traditional box with true end-to-end co-design, this is possible. And in this talk, I'm going to highlight some of the possibilities when you really embrace this extreme co-design approach. So first, let's dive into process. Moore's law is alive and well, but can we amplify it even further? Historically, transistor density improvements, they've been amplified further by gradual increases in die size. And on the right, I've plotted die sizes over the last several decades. And as you can see, there's been a steady increase. But we're hitting a wall now, and die sizes are not really getting much larger. And there's a few primary reasons for this. First, larger chips have low yield. Second, there are some fundamental challenges to lithography that prevent increasing the reticle size. And then lastly, larger chips are more difficult to power and to cool. Now, the industry has been creative in finding ways to extend beyond the single die and solving some of these problems. For example, with advanced chiplets and MCM techniques, we can achieve between 2 to 5 times more silicon in a single device. And recently, we've been really encouraged by early announcements of concepts using very advanced interposer techniques, even some using wafers as an interposer. Such techniques, when they're available, might achieve up to 20 times more silicon in a single device. And we believe techniques like this are highly valuable because they extend the effective size of the chip. But let me show you how we've approached this problem at Cerebras to show that it's possible to push even further with tighter co-design. In 2019, we introduced the wafer scale engine. And earlier this year, we announced the second generation. It's the largest chip ever built at 56 times larger than a single GPU. It's a single piece of silicon. In fact, the largest square you can carve out of a round 300 millimeter wafer. At over 46,000 square millimeters in size, with 2.6 trillion transistors on a single chip, we can fit 850,000 cores. And with all of these cores integrated on a single piece of silicon, we can get some truly mind-boggling numbers for memory and fabric performance. And that's because everything is on chip. To do this required deep co-design to solve the three main problems: yield, process, and power. Yield is an issue even for traditional small chips, so it becomes a fundamental problem for extremely large chips. And at wafer scale, it would be literally impossible to yield a full wafer with 0 defects. Defects in silicon and manufacturing process just can't be avoided, even in mature processes. So to solve the yield problem, we used redundancy. We architected the chip as a giant array of uniform small cores connected with a 2D mesh. And the picture shows an example. Here we have redundant cores and redundant fabric links. The redundant cores are built into the hardware on the top. And on the left, when there's no defects, the redundant cores aren't used. And on the right, when there is a defect, we use the redundant cores to take the place of the defect, and we reconnect the fabric using the redundant fabric links. And this fully restores the logical fabric. With this technique, we can drive yields very high at very low additional cost. But this is only possible because of co-design with the chip architecture. In fact, as you can see, the yield solution is baked deeply into the fundamentals of the fabric design itself. The second major challenge is how to extend beyond traditional lithography limits. And creating larger reticles has some fundamental challenges. So instead, we work with standard independent die on a single wafer. But instead of cutting up these individual chips, we cut out the largest square from the round wafer. And in the standard fab process, independent die are separated by a scribe line. And these are used for mechanical barriers and for test structures. But we add wires to cross these scribe lines to connect these otherwise independent die. And we do this using high level metal layers. This extends the 2D mesh fabric, resulting in a fully homogeneous array of cores across the entire wafer. And this is only possible with a co-design between the fab, TSMC, and the chip architecture. These seemingly simple short wires, they're a big deal. They provide the same bandwidth within a die, but across the entire wafer. That's only possible because we're spanning less than a millimeter of distance on silicon. And for chip designers, we do this all the time without even thinking about it. And when you compare that to traditional SerDes-based techniques, the difference is massive. And it's just physics. Driving bits less than a millimeter on chip is much easier than through a package, connectors, PCBs, and sometimes even cables. And this results in orders of magnitude improvement when compared to traditional IOs, as you can see in the table. We're able to achieve about an order of magnitude more bandwidth per unit area at almost 2 orders of magnitude better power efficiency per bit. But there's a clear trade-off here. And in many ways, by moving the communication problem onto the chip, we've made it easier. But we've shifted that complexity that would have otherwise been in the chip in the form of SerDes, and we've shifted that complexity into the package. So this is only possible with extremely tight co-design with the package and the system. At the package level, we've taken all of that silicon that would have been traditionally physically spread out, and we've moved it all into a central concentrated location, consuming on the order of 20 kilowatts of power. That concentrated high density exceeds traditional power and cooling capabilities. We need to bring the power in, and traditionally, current distribution is done through power planes in the PCB, but the current densities are simply too high to distribute laterally through the PCB. If we did that, we'd only be powering the edges of the wafer. Then we have to bring the power out in the form of heat. And traditional cooling is done through direct airflow. But the heat density is again too high for that to be effective. If we did that, we'd only be cooling the edges of the wafer. So here the solution is to co-design a 3D package. We can bring the current in perpendicular to the wafer by going directly through the PCB, and we can bring the heat out perpendicular to the wafer by using water flow to the cold plates. This solution allows us to power and cool every die evenly, both at the edges and the middle of the wafer. But as you can already see, this isn't your typical package. So it needs to be co-designed with a full system around it. And this is what that looks like. We start with the wafer, which is held vertically. Then it's surrounded by what we call the engine block. That's the subsystem that holds the wafer and the package. where we can bring the power in from the front, again, perpendicular to the wafer, and we can take the heat out from the back through the water in the cold plate and the manifold. And then lastly, we build the system surrounding the engine block, where the entire system architecture was co-designed to support the wafer scale chip from ground up. There are power supplies in the front, right next to the water pumps, and there's a heat exchanger below to remove the heat externally. Power comes in from the front, again, perpendicular to the wafer. The wafer generates the heat, and the heat is removed through the water being pumped through the cold plate and into the heat exchanger below to be removed from the system. And then the cool water is recirculated back to the wafer, forming a fully contained internal water loop. And this is the system. It's a system where every detail is co-designed to enable a chip that's 56 times larger than traditional chips. With this level of co-design between the system, the package, the fab, the chip architecture, we can literally push the envelope of die size well beyond traditional scaling. And we believe new co-designed approaches such as wafer scale chips and other novel packaging are a critical part to solving the grand challenge in front of us. It can enable us to push process gains by as much as 2 orders of magnitude and cluster scale performance on a single chip. But that's only one component of solving this grand challenge. So next, let's look at architecture performance. Imagine what's achievable if we designed an architecture from ground up from neural networks. Neural networks are generally expressed as a series of gem or matrix multiply operations. And this is a valuable and simple way of expressing the computation. And as a result, architectures have evolved to run dense gem operations at higher and higher densities. This has in fact been one of the primary sources of architecture improvement in the industry. It's a big part of that 3 times speed up we've seen in the last couple of years. But can we continue this approach and get orders of magnitude or more speed up going forward? Unfortunately, I think that's unlikely because physical and power considerations means that you can only fit so many Fmax on a chip. And as you build larger and larger gem data paths, the larger the penalty is if your workload doesn't fit the data path exactly. So in fact, as the data paths increase in size, the utilization can actually drop. To get significant gains, we believe you need to change the rules. What if you could get the same results, but with fewer flops? Is that possible? It actually is, because neural networks are naturally sparse. Thinking of them just as dense gems is missing some fundamental properties of neural networks. Sparsity arises when there's a lot of zeros in the computation. And the main operation in neural networks is a multiply add. And we all know that multiply and add by 0 doesn't change the result at all. Sparsity can arise in neural networks for a variety of reasons. Sometimes it's from common ML techniques like ReLU and dropout. And sometimes there's sparsity when you don't even expect it. For example, there are nonlinears that introduce sparsity in the backward pass when the forward pass is otherwise dense. And additionally, even dense neural networks can be made sparse. In fact, inducing sparsity is often done in inference already. And this isn't surprising because from an intuitive sense, neural networks are by definition over-parameterized. And the act of training is, in a sense, really just trying to discover which of the parameters are important and which are not. And the ML community is inventing techniques to exploit this property every day. I've listed a few examples of sparsity algorithms in this table, and they're showing up to 10 times flop reduction, and sometimes potentially even more. So imagine if the architecture could harness this potential and enable the ML community to innovate on yet newer and sparser models. That would be a level of ML hardware co-design that simply isn't possible today. And that's because traditional GEM architectures are fundamentally at odds with fine-grained, unstructured, dynamic computation for a couple of reasons. The first is that traditional architectures use caching and local registers to exploit high degrees of data reuse. And this works really well for dense matrix multiply, which has a lot of data reuse. And it results in relatively low memory bandwidth. The second reason is that these data paths are physically hardwired to perform structured matrix multiplication. Again, working very well for dense matrix multiply because it enables compact and efficient designs. But these become fundamental limitations when there's sparsity, because sparse operations have less data reuse and are unstructured. But what if we could co-design the architecture with sparsity as a first-class citizen and solve these two fundamental constraints, opening up the vast opportunity for ML co-design and sparsity acceleration? There's a large spectrum of ways to handle sparsity at different granularities. But let me show you how we address these two fundamental limitations at Cerebras to demonstrate it's possible to accelerate even the most fine-grained dynamic sparsity. So first, let's look at memory bandwidth. Traditional memory architectures use shared central memory. And it's slow and it's far away compared to the compute performance. Even with advanced bleeding edge techniques like silicon interposers and HBM, the relative bandwidth from memory is significantly lower than the core data path bandwidth. For example, it's very common for the compute data path to have on the order of 100 times more bandwidth than the memory. And this means that each operation, this means that each operand from main memory must be used at least 100 times in the data path to keep utilization high. And the traditional way to do this is by using data reuse through caching and local registers and accumulators. However, there is a way to get full memory bandwidth to the data paths. And that's by fully distributing the memory right next to where it's being used. This enables memory bandwidth that is equal to the operand bandwidth of the core data path. And this is only possible with tight co-design with the system and the machine learning. On the system side, by using wafer scale integration, we can get high capacity at orders of magnitude higher performance without orders of magnitude higher cost or power. But just like the interconnect, this is just physics again. Driving bits that are just tens of microns away from the data path from local memory, all of it on silicon, is much easier than driving those bits through a package to an external device. On the ML co-design side, this level of memory bandwidth enables some pretty remarkable capabilities. With full memory bandwidth, we can run matrix multiplication and all matrix operations at full performance across all blast levels. Traditional architectures with low memory bandwidth, they're restricted to running only gems at full performance. That's matrix multiplies only. In fact, you can see that any blast level below full matrix multiply requires a massive jump in memory bandwidth that's not possible with traditional architectures. But with enough bandwidth, you can enable full performance all the way down to AXP, which is a vector scalar multiply. And that's important because a sparse gem is just a collection of AXP operations, one operation for every non-zero element. And with this capability, it's possible to accelerate any sparse matrix multiply, even for completely arbitrary, unstructured sparsity. So now that we have the necessary memory bandwidth, the second fundamental challenge is how do you handle dynamic, unstructured sparsity? And for that, it's possible to use fine-grained data flow scheduling techniques, where all the computation is triggered by the data. In the Cerebrus core, the fabric transports both data and associated control in the hardware. And once the core receives the data, it triggers the tensor instruction to run. With this data flow mechanism, the entire compute fabric is a data flow engine. And this enables native sparsity harvesting by simply filtering out all the zero data at the sender. Since all the compute is triggered by the data, if the sender doesn't send any data, the receiver doesn't perform any compute. It's that simple. Not only do we save the power because we're not performing the wasted operations, but we can get acceleration by skipping the wasteful work and using those cycles to perform the next useful work. And this is possible only with tight co-design with the machine learning and the compiler and kernel software. On the machine learning side, this natively accelerates natural sparsity, but it also enables co-design of new sparse ML models. And on the software side, we co-design the software to be data flow aware from the ground up. And to illustrate that software co-design, let's look at a sparse matrix multiply as an example. We can consider the entire wafer as a single giant sparse matrix multiply array. And here's how that works. We start with activations distributed across the wafer's on-chip memory. Then we stream the weights through. And as they stream through, they trigger multiplication with local activations, one individual weight at a time. And this is where we're using that fine-grained hardware data flow mechanisms built into the core. This is where we're performing one axis vector scalar multiply for every weight as it streams through, and we're skipping all of the zeros. And the full memory bandwidth is what's enabling all of this at full performance. The resulting partial sums are then accumulated using the high bandwidth fabric across the entire wafer, and there's no need to block or partition the matrix because of the sheer size of the wafer. We can operate on the full range of matrix sizes. And all of this is the same flow for both dense and for sparse. And here are some of the results that we've measured. In our lab, we've measured speed up for fully unstructured weight sparsity on GPT-3 size layers, all the way up to 90% sparsity, which is 10 times more zeros than non-zeros. And on the right, you can see in our lab results that we are getting near linear speed up even at these extreme levels of sparsity. The only limitation really is just Amdahl's law and the cost of amortizing those fixed overheads. But with our high memory and interconnect bandwidth, we're able to reduce all of those overheads significantly, as you can see in the results. And those overheads reduce even further as the model grows. So these results, they demonstrate that we can accelerate fully unstructured sparsity, which is not possible in traditional GEM data paths, and therefore accelerate all types of ML sparsity algorithms already being used today, as well as enable a new class of smarter, sparser models that are actively being developed. As a community, it's through this level of ML co-design that we can practically reach extreme scale models, and we can break free from the traditional brute force flop scaling. In fact, we believe that sparsity opportunities, they only increase as the model size grows. So coming back to the grand challenge in front of us, with techniques like sparsity to enable deep ML co-design, along with traditional architecture improvements, there is a path to driving an order of magnitude or more of architecture performance. By changing the rules, we can go beyond just flops. And we can enable an entirely new class of sparse ML techniques co-designed with the ML community that's not possible otherwise. All right, we've addressed 2 out of the 3 major components to scaling performance. So let's talk about the last one, cluster scale out. Cluster solutions, they exist today, but it's still hard to scale. Why is that? To understand why, let's look at existing scale out techniques. The most common is data parallel. Here, a model is replicated in each device, and training data is split across the devices. This is the simplest approach, but it doesn't work well for large models because the entire model needs to fit in each device. So to solve that problem, a common approach is to run model parallel. And here you split the entire model across the layers, and you run different layers on different devices as a pipeline. This enables larger models, but has significantly higher communication overhead. And as you spread across more devices, the activation memory increases quadratically because you need to keep all the activations in the pipeline. So to avoid that, it's also common to run another form of model sparsity by splitting the layers across devices. But this also has communication overhead, and splitting the layers is complicated. And so because of all of these constraints, there's not only a single one-size-fits-all way to scale out today. In fact, in most cases, training massive models requires a hybrid approach where you use both data parallel and model parallel. That's actually how OpenAI trained GPT-3, for example. So although scale-out solutions technically exist, there are so many limitations and they're so complicated that often they're not accessible to the ML community. And the fundamental reason for this is actually pretty simple. In traditional scale-out, memory and compute, they're tied to each other. Trying to run a single model on thousands of devices turns the scaling of both memory and compute into distributed constraint problems that are interdependent. As the model size grows, we need to do more partitioning of the model onto more chips and do more fine-grained coordination and more synchronization. If you've trained a neural network on a large GPU cluster before, you'll know what I mean. And in fact, large companies like Google and Microsoft, they often have entire engineering teams to figure out how to do this. To solve this problem properly, I believe it's not about creating software solutions to hide that complexity, but by truly co-designing the solution at the cluster level and thinking outside the individual device. It's possible to architect a solution that's inherently simple and scalable. Let me show you the approach that we took at Cerebras to demonstrate what's possible. It's possible to think of the entire cluster as the ML accelerator, and then to architect the cluster level memory and the cluster level compute in a more natural and scalable way. At Cerebras, we're doing this in an execution model we call weight streaming. We first separate the memory from the compute, fundamentally disaggregating them. And the reason we can do this is because neural networks use memory differently for different components of the model. So at the cluster level, we can design a purpose-built solution for each type of memory and each type of compute. And as a result, we can untangle them and completely simplify the scaling. So let's see what this looks like. We start with the primary compute unit, which is the Cerebras CS2 system. With a single large wafer, it's the foundational building block on which all large model layers can run without partitioning. And next, to handle these models of extreme size, we add an external store to hold all of the model parameters, or weights. We call this technology MemoryX. And it's designed specifically to scale to extreme model sizes, capable of supporting up to trillions of neural network weights. And next, completely independent of that memory, we introduce an interconnect to scale up the number of CS2 systems. We call this interconnect technology SORMX. And it's also specially designed to scale neural network training compute to cluster up to 190. In this execution model, all of the model weights are stored centrally in the MemoryX unit. And then they're streamed onto the CS2 system as they're needed to compute each layer of the network one layer at a time, The weights are never stored on the CS2, not even temporarily. As the weights stream through, the CS2 performs all of the computation using the data flow mechanisms, and the resulting activations stay resident on the CS2, ready for the next layer. And then on the backward pass, the gradients are streamed back in the reverse direction back to the memory X unit, where we do the weight update. So you can think of this as designing a purpose-built memory hierarchy at the cluster level. And to do this, we need to architect a solution to be latency tolerant, since in general, moving data further from the compute can hurt performance if you're not careful. But as I said, not all memory in neural networks is being used for the same thing. Activation memory has to be accessed immediately by the next layer, making it latency sensitive, so we keep it on chip. But weight memory, on the other hand, is used and updated relatively infrequently. There's no back-to-back dependencies. And so we exploit these properties by doing two things. First, we use coarse-grained pipelining to avoid the dependencies between layers by scheduling the entire training as a pipeline of layers. We start streaming one layer without having to wait for the previous layer to complete. And as with any pipeline, this enables high performance that's not latency sensitive. And second, to cover the dependency between training iterations, we actually overlap the weight update with the forward pass of the same layer. This forms a fine-grained pipeline of the updated weight matrix with the forward pass that's consuming it. And since the CS2 is processing the weights individually, we can stream out the weights immediately after they're updated so that the forward pass can proceed without having to wait for the entire weight matrix to be updated. By using these pipelining techniques at the cluster level, the weight streaming execution model can hide the extra latency from external weights and hit the same performance as if the weights were locally stored on the wafer. To solve the problem of storage capacity, this architecture moves all of the model parameters into a single external device called memory X. And by moving the memory further away from the compute, it's possible to use both DRAM and flash storage to support extreme model sizes in a single subsystem. It also has internal compute to perform the weight update and optimize its functions. Just like we did for memory, we're separating out the compute that's operating on the weights and we're putting it close to the weights. Since these weight computations are extremely small compared to the main model execution, we can efficiently perform these updates externally while the main model runs in parallel on the CS2. And with this approach, we can provide flexible capacity to store up to even these extreme scale models. And then we can scale the compute completely independent. This is done by simply clustering multiple systems with a specially designed interconnect for data parallel. We call this SwarmX. And it sits between the memory X units and the CS2 systems, but it's completely independent from both. SwarmX broadcasts weights to all the CS2s, and then it reduces the gradients from all the CS2s. So in that sense, it's more than an interconnect. It's really an active component in the training process, purpose-built for scale-out training. Internally, SwarmX uses a tree topology to enable modular and low overhead scaling. And because it's modular and disaggregated, you can scale to any number of CS2 systems with exactly the same execution model as a single system. Scaling to more compute is as simple as adding more nodes to the SwarmX topology and adding more CS2s. And lastly, since the underlying architecture supports sparsity natively, the cluster also supports sparsity natively. Sparsity is induced in the weight matrix in the memory X unit by using one of the ML techniques I mentioned. And then these sparse weights are streamed to the CS2. The SwarmX interconnect broadcasts them in sparse form. And then when the CS2 receives them, it performs the computation in sparse form using the underlying data flow mechanisms. All of this happens natively with no change to the weight streaming execution model. In fact, it's exactly the same flow as for dense. With this interconnect technology, in combination with the pipelining techniques I described, we project near linear performance scaling from a single CS2 to 192 systems. And here's how that scaling translates to training speed up for a range of natural language models from 10 billion parameters all the way to 100 trillion parameters. This is using the scaling laws for MLP models published by OpenAI. And for reference, the largest language models today, like GPT-3, are around a few 100 billion parameters. As you can see, the scaling is near linear and mostly falling off for relatively smaller models where batch size becomes a limitation at a certain point. But for larger models, especially these extreme models, we project near linear scaling all the way to 192 systems. So as you can see, by changing the rules, by thinking beyond the individual devices and thinking holistically at the cluster level, it's possible to solve the fundamental challenges of scale out today. And it's possible to execute exactly the same for a single device as for hundreds of devices. And that's how it's possible to address the final component of the grand challenge in front of us. Scale out that's actually inherently scalable. So now let's go back to where we all started today. In the past couple of years, we've seen over 1,000 times greater demand from the ML workloads, and there's no end in sight. So in the next couple of years, this is where we will be. And on first glance, this seems daunting, maybe not possible. But what we've seen today is, in fact, it is possible. But not by using traditional techniques. Only if you change the rules. Only if you think outside of the traditional boundaries. That future is achievable. Only with tight, deep co-design, it's possible to do some truly remarkable things. It's possible to build chips beyond individual die, to push compute beyond brute force flops, and to design an architecture with inherently cluster scale performance. What a truly exciting time it is to be a computer architect. I've shared some of the approaches we're taking at Cerebras to pursue this future, just as an example of what's possible. And I'm really looking forward to seeing what we as a community will come up with next. Thank you very much.
Thank you, Sean, for that amazing talk and the constant reminder of co-design throughout. We have a number of questions throughout. I'm going to hop around and ask, and let's get started. We've got the first question: are bigger models always better? To rephrase, should the community also focus on reducing model size where possible?
I think that's a great question. I mean, probably in general, the jury is probably still a little bit out in terms of the gains that you get from different model architectures versus simply increasing the model size. But in a few domains, especially like these natural language domains, it's been shown that just simply increasing the model size continues to show increased performance of the models. Now that might not hold across, all the other domains as well. I think this is an open question that the ML community is working through. But it's remarkable how well natural language models scale. And we're starting to see some of those trends in vision as well. So, I think coming back to this co-design point that I've been stressing all throughout the talk, I don't think that just blindly scaling to larger models is necessarily always the right thing. In cases where that's been shown to have tremendous value, we as an architecture community need to find ways to do that. I think sparsity is one of the key ways. But we also need to explore other ways to do ML co-design to enable, architectures, model architectures that might not be possible today. I think that's a very rich field that we need to be exploring as well.
We've got a question from Mahmoud Nadaran. With respect to fab modifications, how many additional steps were taken to create a wafer scale chip compared to traditional die-based chips?
So from the chip design side, within the single reticle or a single die, very few modifications were done, as you might expect. And that was intentional because we want to fit within the existing process as much as possible. However, at the fab level, when you need to integrate these individual dies together, we actually did have to change quite a few steps within that process. Specifically, being able to span the distance between the die required not just a special mask that allows us to to create those wires, but also a change to the fab process, because those scribe lines that you're covering with those wires are actually used for things like test structures at the fab, right? Which typically chip designers don't see. These are things that the fab uses to control and to monitor. And so it required a tight collaboration and co-design with the fab to work out the process so that we can, in fact, at the right stage, cover those test structures with the high-level metal layers.
We have a question from Emre Ozer. Thanks for the great talk. How adaptive is the massive wafer scale ML hardware architecture? What I mean is how much it depends on the deep neural network models. If tomorrow the ML community comes up with a brand new model, a non-neural network based one-shot learning, can the wafer scale chip architecture be adapted to such dramatic ML paradigm shifts?
I think that question is great because it's getting at one of the fundamental challenges of building an accelerator, right? Fundamentally, an accelerator is getting some of its benefit and advantages from building something that's special purpose. But then on the flip side, you also don't want to build it so that it's hardwired to only perform a single operation, because especially in the ML space, as the workload is evolving and changing at a rapid pace, you need to have enough flexibility, enough programmability, generalizability in the architecture itself to be able to adapt. And so I think that is the crux of building and architecting an accelerator. It's not an easy question to answer because finding that right balance is admittedly quite difficult, especially in a workload environment that's still shifting. But our approach has been to build all of the components to be fully software programmable. So in fact, I talked about a matrix multiply as an example, but there isn't actually anything built into the hardware that even performs matrix multiplication. The only underlying hardware capabilities are all based on accelerating tensor processing. And then it's up to software to combine those tensor operations to perform the final operation that's desired by the workload. And so we believe that strikes a very good balance between getting the high performance and purpose-built acceleration, but without making it too narrow and too special purpose, that as the ML evolves, that we can still adapt to it.
We have a question from Jia Huang. Are the process technology amplifications attributed to the on-chip interconnect density improvement over the off-chip interconnect, rather than much more chips on the wafer compared to a traditional package?
I'm not sure if I fully understood the question, but let me try to explain our thinking behind how we expand our fabric beyond a single chip. So the philosophy is really build as much fabric bandwidth as you need to be able to solve the problem within a single chip. And so we basically put enough fabric bandwidth such that we can map, the various different workloads, as well as, some variations beyond what we're seeing right now, right? That was the criteria for determining the fabric bandwidth within a chip. And then all we did was we extended that fabric bandwidth across the entire wafer. And again, that was only possible because with the wafer scale integration, we're able to get the wire density that's sufficient for us to be able to extend that on-chip bandwidth. But it was kind of driven bottoms up, so to speak. Not sure if that answers the question, but hopefully gives you an idea of how we, our design process.
We have a question from John Calamatianos. Could you comment on how to further improve scale-up performance for such a wafer-based machine? Can you comment on how the AI core utilization changes with different sparsity levels?
Yeah, so on the first question, scaling up, going from a single traditional chip to a wafer scale chip is kind of one really big step function. And then the natural question is, well, where do you go from there, right? And I think there are the obvious one is you could potentially build larger wafers, but we see that the industry has pretty much settled on the 300 millimeter wafer as probably being the largest wafer that we will see in a long time. And so scaling wafer size doesn't appear to be the most practical way to continue to scale up. We believe that there's other advanced packaging techniques that will allow us to scale further than a wafer. For example, by using other substrates as an interposer, you may be able to bridge even multiple wafers. And so these kinds of ideas, we believe the industry needs to continue to pursue. Definitely we at Cerebras are very much pursuing, but we need to continue to find ways to pack more silicon more tightly together. And the second question, I think, was about utilization and sparsity, right? Mm-hmm. On that question, I think, as I mentioned and showed in that one performance slide, as you increase sparsity, this is just a fact of life, the parts of the computation that don't scale with sparsity, they become more and more dominant. And so it becomes a challenge and architecture goal of designing in all the right mechanisms to be able to reduce that fixed overhead. And in our case, what we rely on very heavily is an extremely high memory bandwidth as well as the interconnect bandwidth to be able to perform fixed overheads like partial sum accumulations, for example, at an extremely high performance so that they don't become dominant. But it's a very interesting kind of transition, because when you are optimizing for dense workloads, it's all about optimizing the MAC and the multiply accumulate, because that's almost all of the work. As the workload gets sparser and sparser, it becomes more about optimizing for the fixed overheads than necessarily just optimizing for the multiply and accumulate.
I'm going to combine a couple of questions. Eric Altman, to do all of the co-design behind the work, did most of the team have expertise across multiple areas, from wafer design to architecture to packaging and thermal design to ML algorithms? And as part of this work, what sort of rule changes did you have to verify the beast that's being that you guys have built?
Yeah, so on the first part, so the general answer is yes. We to be able to do this kind of end-to-end co-design isn't easy, right? And in large part, it's because you need to innovate and invent across the board in all of these different areas, all the way from collaboration with the fab to to chip design, to package, system design, all the way into the software compilers, into the machine learning. And what makes this perhaps even more challenging is that even areas that you might traditionally think are not areas you need to innovate because you can use off-the-shelf solutions, when you've changed the equation enough, oftentimes those don't apply anymore. So that question is absolutely, I think, getting at the heart of what makes this challenging. And so at Cerebras, to solve that, we have basically built a team with experts across the board in all of those areas. And it's not about just knowing what is done today and in the past, but it's about being able to innovate and invent on top of that. And that I'll be honest is is a non-trivial thing to do, to be able to pull together the right team and the right sets of experts to be able to pull this off. The other question is what kind of validation is done, correct?
Yeah.
That's a very interesting problem, and is actually perhaps amplified by the scale of what we're building. Sometimes we internally had referred to this as there's like this 1,000,000x challenge. Is that traditionally one of the ways that you can validate is through simulation. But suppose we're 1,000 times faster than existing hardware, and the simulator is 1,000 times slower than existing hardware. You got a 1,000,000x gap that you need to bridge, and that's what makes it fundamentally quite challenging to validate. But our approach has been to take a hierarchical simulation and validation approach, and so we have various levels of simulators, from very low level simulators that we use to validate at the core level, to more abstract simulators to validate the software interactions with the hardware at the compute fabric level, and then yet even higher level simulations to model and to validate at the system level. But ultimately, it is a challenging problem.
Thank you. I was just made aware that there are more questions on Huva. I'll ask one or two more questions. I know we're into the break, but there's a question here by Gaurav Kaul. Would streaming be mostly beneficial for very large weights or activations? What is the threshold and the latency of the interconnect?
So the weight streaming technique generally works quite well for larger models, but these larger models don't necessarily have to have extremely large weights. For example, there are models, a kind of a trivial example are like convolutions, where the model is actually very large from a compute standpoint, but the weights might be relatively small. In all of those cases, this weight streaming model works quite well, because again, what it's doing is exploiting the fact that you're able to use these weights relatively infrequently, do a lot of compute on them once you stream them into the wafer, and then you don't need to touch them for quite some time, right, before you come back to them later on in the model training. And so what we found is that ultimately large models is where this performs the best, and where we run into the need for slightly different execution models are for extremely small models. But again, that's not where our focus has been. And so it's our weight streaming execution model is able to cover quite a large portion of the workloads that we see right now that are commonly used.
I'll ask one last question, and I will send you a list of these questions later on. We'll post them somewhere so that you can answer them. But what are your perspectives on wafer scale like Cerebras versus chiplet-based scaling like Tesla's Dojo from a perf or cost perspective?
So as I mentioned, I'm actually quite encouraged by advanced announcements by Tesla on their Dojo approach. I think in spirit, it's trying to achieve a lot of the same goals that we're trying to achieve. And as I've been trying to stress in this talk, I really believe that we as an industry need to be doing more and more of that to be able to meet this unprecedented demand. And so in that sense, I'm very encouraged, and I think that what they're doing is very worthwhile. But where I see a kind of a critical architectural or technical difference is that by still relying on traditional SerDes to perform the connections between the die, you're actually giving up quite a lot of performance, and you can literally see that by looking at the gaps that are the white space gaps in the actual physical layout. And so I believe they're doing that primarily so that they can put together a collection of known good die. It's their way of handling yield, I believe. And so if you have an alternate way of handling yield, like we do, then we believe that taking that overhead isn't warranted. But largely speaking, I'm very excited and support that kind of innovation, because I believe we need to do more of that as an industry.
Thank you, Sean, for the amazing talk. And I will hand it over to Dimitri to end this portion of the session. And go ahead, Dimitri.
Thank you.
Sean, thanks a lot for the excellent keynote, which attracted a lot of attention and questions. This is a small token of our appreciation, a certificate of appreciation, which of course we will email and also mail to you afterwards. Thank you very much.
Thank you very much. My pleasure.
We now have a short break before the award ceremony in about 5 minutes. Sean, the GatherTown link is there. If you can hop on in there for those whose questions were not answered, if they come to you, please try to do so. I will forward the questions to you in email, and if you can try to respond to them, we'll post them back onto the platform later on. Thank you so much again for a wonderful talk. Really appreciate it.
And we will be back in 5 minutes, starting the award session.
Yep.
Bye, everyone. Thank you very much.
Thank you.